Swayam Prabha. Digital India. Educated India.
So, welcome to the 21st lecture on the cryogenic engineering under the NPTEL program. Just to give a brief of what we did in the last lecture, I will just summarize some points and then we will go to the topic of our gas separation. Last time we had studied Gibbs phase rule, which is basically given as F is equal to C minus P plus 2, where F is degrees of freedom or the intrinsic properties requirement to be specified for any mixture. C is a component and P is number of phases. Also, we understood about the temperature composition diagram and it gives a variation of mole fraction, that is Y, with temperature T at constant temperature. So, when we talk about any mixture, the number of phases are 2 if we are talking about two phase mixture or mixture separation by lowering of temperature. We got two components and therefore, we require some degrees of freedom or the values of F in there. If you got a two components, two phases or a single phase, we require a particular number of properties to be specified. Whenever we talk about a mixture, what we require is a mole fraction Y to be specified of a component A and component B, and these are very important diagram. These are very important relationship which have to be known in order to specify a mixture. For example, two component, two phase, we need to have two values to be known to us. We need to have two degrees of freedom, which could be pressure and mole fraction, or temperature and mole fraction for a given pressure. When a mixture condenses or boils, that means when a change of phase happens, there is a change of temperature, and this is a non-isothermal process, which we saw last time, that during condensation of a single component, the temperature remains constant. During the phase, the temperature remains constant, which is true with condensation as well as for boiling. However, for a mixture, we have seen during the last time when I had presented the temperature mole fraction diagram or TY diagram, we have found that during the change of phase, the temperature decreases, which means that the process of condensation or boiling is not a isothermal process. It is a non-isothermal process, which is a very important deviation from what we have been learning from normal one component system. We also found that the repeated rectification of a mixture enriches the liquid and vapor phases with high and low boiling components respectively. We had seen that when the mixture is being condensed or vaporized repetitively, what you get ultimately is a high boiling component liquid at high boiling component, and slowly we get on repeated rectification process, we get a vapor phase getting richer and richer in the low boiling component. For example, we had seen for oxygen nitrogen mixture that when you go on rectifying in repetitive manner, the liquid will get richer in oxygen, or what you get is a liquid oxygen at one end, which is 100% oxygen then, and the vapor phase will get richer in nitrogen gas, nitrogen vapor. So, ultimately what we do is basically condense this vapor in order to get liquid nitrogen. But what is important is to understand that the one phase, the liquid phase gets richer in a high boiling component, which is oxygen for a nitrogen oxygen mixture, and the vapor phase get richer in low boiling component, which is nitrogen in this case. So, in the earlier lecture, we have seen the temperature composition diagram, and we also introduced those diagrams, how they can be exploited to understand the rectification process, which happens in actually a rectification column. These diagrams form the basis of rectification process. The molar concentration of vapor and liquid phases of a two component, two phase mixture change with temperature. This is what we saw. At every point during condensation, during the phase change, we saw that the vapor phase get richer in low boiling component, while the liquid phase getting richer and richer in high boiling component. This is what we just studied in the last slide also, and this is what exactly happens as the temperature gets reduced. The vapor phase will still get richer in the low boiling component, and the liquid phase will still get richer in the high boiling component. Hence, because these diagrams are so critical, because these mixtures have to be ultimately separated from in the rectification column, what is important is to understand the basic laws which govern these mixtures, because these are going to be used every time. So, hence what we understood is there is a need to study various laws governing the properties of the mixture, and therefore, in this particular lecture what we are going to study is mostly the properties which govern this mixture. Outline of this lecture is we will have to study the Dalton's law of partial pressure, which possibly you must have studied that. We will have to repeat this again for mixtures now. Then very important law is the Raoult's law, and then we got a Dalton's law plus Raoult's law also. Then we also got a Gibbs-Dalton's law, and then we come to understand what is the basic significance of a distribution coefficient concept. What is this? How does it play a very important role in a rectification column, theoretical analysis? And finally, all these things could be understood better when we got some tutorials. So, I got 2 tutorials where you can understand the application of these laws from gas separation point of view. So, let us come to Dalton's law. The Dalton's law was formulated by an English chemist, John Dalton, in the year 1801 for gas mixture. So, it is a very old law. You can see that it is almost 200-year-old law basically, and it has definitely been applied over a period of time for gas mixtures. It relates the partial pressure of an individual component of the mixtures. Mixture has got various components, and various components will be in the mixture in different proportions. The molar fraction will be different, and the partial pressure therefore will be different of each component in a given mixture. Dalton's law relates basically this partial pressure to the total pressure of the mixture, and we will see now how it does. So, this relates the partial pressure of an individual component of the mixture to the total pressure of the mixture and to its mole fraction. It is a very simple law. I am sure you must have studied this law earlier, but mathematically I will relate this law to the total pressure of the system. It is applicable only to non-reacting ideal gas mixture. So, this is a very important thing, that we will not come across non-reacting ideal. Our mixtures will be real mixtures. So, this will basically govern the ideal gas mixtures, but we can formulate it for real mixtures also. So, simple illustration is, consider a mixture of 2 non-reacting ideal gases. So, ideal gases being gas A and gas B at a temperature T. So, I have just shown a small cylinder where gas A has got some component, gas B has some component, and in this mixture, as you can see in a given enclosure, that we have got some component of gas A and some component of gas B. Let the total pressure of the mixture be P total, and the partial pressure of gas A and gas B be PA and PB. Because they are present in partiality, the total pressure is P total, and depending on the presence or amount of gas A and gas B, it will have its partial pressure, which could be PA and PB denoted respectively. Also, the YA and YB are the mole fractions of gas A and gas B. So, how much mole fractions? If they got a 0.2 mole fraction of YA and 0.8 mole fraction of YB, or thing like that, depending on how much quantity of gas A and gas B is there in a given enclosure, which will decide the molar fraction of YA and YB. By Dalton's law, the total pressure of the mixture is equal to the sum of the partial pressure of the individual components. So, it is a very clear and simple law that P total will basically depend on the sum of partial pressure of individual component, that is PA and PB. So, mathematically I can write P total is equal to PA plus PB. This is the total pressure of the mixture is equal to the sum of the partial pressures of gas A and gas B, as you can see from here. Also, the partial pressure of each component is directly proportional to its mole fraction. So, if I want to compute the value of PA, the PA will basically depend on what is the value of YA, PB will depend on what is the value of YB, and mathematically PA is going to be equal to P total into YA, and PB is basically equal to P total into YB, and this is, so what we can say is PA is directly proportional to YA, PE is directly proportional to YB, and the constant of proportionality could be P total in both the cases. So, once I know what is my mole fraction of YA and YB, or a gas A and gas B, and if I know the total pressure of the mixture, I can compute PA and PB directly, and that is what the Dalton's law of a gas mixture. It will give us conversion of molar fraction to PA and PB for the partial pressures, and then what you can compute is a P total. Extending it to general statement to the mixture of n components, we will have following, that the total pressure P total is equal to sigma Pj when j is ranging from 1 to n for a n component mixture. I think this is very simple and clear. And the partial pressure of the jth component is given by Pj is equal to P total into Yj. So, depending on the value of mole fraction of a jth component and depending on the value of P total or the pressure of the total pressure of the mixture, you can compute the partial pressure of jth gas, jth mixture, jth component. So, where Yj is the mole fraction of the jth component. So, one can find out the partial pressure depending on the molar fraction, and if we know the partial pressure, we can find out the total pressure of the mixture. Now, extending further from Dalton's law, having understood the basic of Dalton's law, now we will go to Raoult's law, which is also a very important law to understand the properties of mixture. So, let us come to now Raoult's law. Now, consider a simple one component two phase mixture in a thermodynamic equilibrium as shown here. So, again in an enclosure, we got a two phase system. That means, we have got some liquid, the component is A or a gas A, and we got some liquid which has only gas A as a component. You will have some vapor pressure basically, you will have some gas A component above this liquid in an enclosure. So, what you have is basically a two phase mixture in a thermodynamic equilibrium each other, but it is a one component mixture. It is not a mixture actually, it is a one component system which has got only gas A as the component. The vapor above the liquid phase exerts a pressure and this is called as vapor pressure. As you know, a simple vapor pressure basically is a function of the temperature. So, if I know the temperature, I can compute the vapor pressure for a two phase system. So, as I just said, it depends only on the temperature of the system. If I know the temperature entropy diagram, I can compute, if I know the temperature, I can find out on a dome what is my saturated vapor pressure at that point on a dome. This will give me the vapor pressure of that component for a given temperature. We will see this again in tutorials later. So, similarly now, we have just seen a system of one component. Let us now look at a system of two components and two phase mixture in thermal equilibrium as shown. So, here you can see the upper illustration is only for gas for component A, but now I have got two components here which are A and B, and again it is a two phase system, and therefore, both the components are in liquid phase as well as on a vapor phase above the liquid, and they exert a vapor pressure on this liquid. So, they are in thermodynamic equilibrium with each other, but it will have different vapor pressure depending on the temperature of the mixture. So, the components are assumed to be ideal, that means there is no intermolecular forces and chemically non-reacting. So, non-reacting is a case must, but what is important in ideal consideration is there is no intermolecular forces. Such a mixture is called as an ideal mixture or a perfect mixture. The Raoult's law basically holds good for perfect mixture or ideal mixture. The real mixture will deviate away from the Raoult's law, and therefore, this deviation has to be understood, because in real mixture we will have intermolecular forces, and these have to be considered if you want to really compute to a very high degree of real analysis. If you want to do, in that case we will have to take into consideration all the intermolecular forces. It is clear that the vapor above the liquid has both the components. So, in liquid condition also we got A and B, in the vapor condition also we will have A and B. The Raoult's law was formulated by a French chemist Francois Marie Raoult in the year 1882. So, this law also is a very old law, almost again 130 years or something like that, and this law also has been applied over a period of time, and therefore, its importance has been well understood. So, consider a perfect mixture of gas A and gas B in thermodynamic equilibrium at temperature T, and let gas A as following parameter. So, the parameters associated with gas A are PA, which is its partial pressure, XA is a mole fraction in liquid phase. Now, you got a liquid phase coming into existence. Till now, in the Dalton's law, we talked only about the gas mixture itself. Now, we are talking about both liquid and vapor over here, and therefore, the component what we identify in liquid is XA. So, XA is a mole fraction in liquid phase, while Ya is a mole fraction in the vapor phase. So, because we have got both the phases over here, we have got a concepts of X and XA and Ya. Similarly, we will have XB and YB for gas B. We will not talk about that right now, we are talking about only gas A. And pi A is a very important parameter, we have just talked about this also earlier, which is the vapor pressure at temperature T. Now, this is not for a mixture we are talking about, this is independent or a characteristic of any component. For a gas A, if we know temperature, we know the vapor pressure at that particular temperature. So, pi A is the one which gives me vapor pressure of gas A at temperature T. Alright. So, we got a four component, which is the partial pressure, mole fraction in liquid phase, mole fraction in vapor phase, and pi A is the vapor pressure at temperature T. Now, basically I would like to relate all these things. not only for gas A but for gas B also. How do I relate them? Raoult's law relate this parameter, and therefore, let us see that in next slide. So, the statement of Raoult's law is that the partial pressure of a component in the vapor phase is directly proportional to the mole fraction of that component in the liquid phase. So, what is the partial pressure of a component in vapor phase? Is Pa, and this is directly proportional to the mole fraction of that component in liquid phase. We just found that Xa is the mole fraction of that component in liquid phase. So, basically the Raoult's law relates the partial pressure in the vapor phase, which is of this component, let us say gas A, above the liquid. The vapor pressure will be only for the vapor which is above the liquid, and the vapor pressure exerted by gas A or gas B is related to the mole fraction of that component in the liquid phase. So, vapor pressure Pa is going to be related to Xa. Xa is the mole fraction of that component in the liquid phase. So, my mathematical statement therefore becomes P is a function of Fx, which is what we just talked, which is P is a partial pressure and function of x. And what is x? X is a molar fraction of that component in the liquid phase. So, for gas A, now if I apply this law for gas A, I will get Pa is equal to pi A Xa. It's clear. Here Pa is related to Xa, and what is that constant of proportionality? It is the vapor pressure at that temperature, at the mixture temperature. So, Pa is equal to pi A Xa is a very important result as to which is coming out from this Raoult's law statement. I am relating the partial pressure of a vapor in a given mixture to the molar fraction of that component in liquid phase, and it is basically getting related by the vapor pressure of gas A, which is a characteristic pressure at a given temperature of mixture. Alright. So, if I know Xa, I can compute its partial pressure exerted by the vapor of that component in a given mixture or in a given enclosure at temperature T. Similarly, for gas B, if I apply the same rule for gas B, I will get partial pressure exerted by vapor component B on this mixture of A and B, and it is related to the component Xb, and corresponding to gas, the value of pi will be pi B, which is the vapor pressure of gas B at the temperature T. This is a very important relationship between Xa and Pa and Xb and Pb. Extending it to the mixture with n components, we have just seen what is the value of Pa and what is the value of Pb. If I talk about n components, I will have partial pressure of a jth component given as Pj is equal to pi j xj. Same thing, not A and B anymore, but I am applying it basically for any jth component if you have got n number of components in a given mixture, where xj is the mole fraction of the jth component, pi j is the vapor pressure of the jth component at temperature T. It's clear. I am just generalizing what we studied earlier. Now, we have just studied Dalton's law, we have now studied Raoult's law. If we combine both the laws for a given mixture, what we get is a very important relationship now. If the vapor above the liquid phase is assumed to be ideal, because you know Dalton's law is basically meant for gases, vapor is not gas. But if I assume that vapor above the liquid phase is assumed to be ideal, then combining the Dalton's law and the Raoult's law, what we get is two things. I will just put in Dalton's law, I will then combine it with the Raoult's law. If I say Dalton's law, what I know is the P total is equal to Pa plus Pb. The total pressure is equal to the sum of the partial pressure, which is a Pa plus Pb. And what I get from Raoult's law is the value of Pa and Pb. So, Pa is equal to pi A Xa and Pb is equal to pi B Xb, where Xa and Xb are the molar fraction in the liquid of component A and component B respectively, while pi A and pi B are the vapor pressure of those gases at a given temperature. So, now I can basically relate the P total to this Pa and Pb, taking the value from Pa and Pb. So, what my expression will be? So, P total, I will just replace this Pa by pi A Xa plus pi B Xb. So, what I am doing is basically I am relating the total pressure to the Xa and Xb respectively, to the molar fraction of component A and component B in a given mixture in the liquid Xa and Xb. So, extending further for the liquid phase, the following statement now holds good, which is we know that Xa plus Xb is equal to 1. Alright, the molar fraction sum in a given mixture is going to be equal to 1, and P total, what we have just seen, is equal to pi A Xa plus pi B Xb. If I just now replace this Xb is equal to 1 minus Xa and put it here in this expression, what I get is P total is equal to pi A Xa plus pi B into 1 minus Xa, obvious. And therefore, I can do the otherwise also. I can put x a is equal to 1 minus x b in the same statement. So, my p total is equal to pi a into 1 minus x b plus pi b x b. I am just replacing the value of x b in this expression and the value of x a in this expression. And now, I would like to put this graphically, and this is what in short the Raoult's law will be. So, you can see that I got two axes on which the p is mentioned, and I got two end points of x axis on which I have given a mole fraction of x a. So, if I go from x a is equal to 0 to x a is equal to 1, which is 100% a, and I got x b is equal to 0 and x b is equal to 1 here at two ends. At in between values, I got some value of x a. For example, here I got x a is equal to 0.25 and x b is equal to 0.75. Here I got x a is equal to 0.5, x b is equal to 0.5. Here at the end I got x a is equal to 1 and x b equal to 0. That means 100% a exists over here, 100% b exists over here. What I am plotting on this is basically P A and P B. So, P A is nothing but pi A x a, which is given in a red color over here. So, the vapor pressure, partial pressure of P A at A is equal to 0 is going to be 0, while A is equal to 1 is going to be maximum. So, P A ranges from 0 to P A max here. Similarly, the partial pressure of B will range from 0 to max here, and the total pressure is at every point is P A plus P B. So, at the two end points, the total pressure is equal to, in fact, P A is equal to 0, and therefore, P total at this point will be equal to P B, while the P total at this point will be equal to P A. And at every intermediate point, we will get algebraic sum of these vertical heights, which is given by P A plus P B, and this is my P total. So, P total at every point is going to be the sum of the partial pressures of P A and P B, which is what we have understood from Dalton's law and Raoult's law. So, this in actually just graphical representation of the Raoult's law and the Dalton's law, all right. So, I think just to understand in more graphical format, this will help, and the values of P A and P B are related to x A and x B by the Raoult's law, which is what we just saw. Now, going ahead from here, I got one more law, actually just a deviation of the Dalton's law. It is called as Gibbs-Dalton's law. Again, assuming the vapor pressure above the liquid to be ideal. This is what we did earlier also. Gibbs-Dalton's law is application of Dalton's law to this vapor. What is this showing? Basically, I am applying Dalton's law for this vapor, assuming that the vapor above are behaving ideally, like ideal gas basically. So, Gibbs-Dalton law is nothing but application of Dalton's law to this vapor. So, let P A and P total be the partial pressure of gas A and total pressure of the mixture respectively, which is what we have seen earlier also. Let Y A is the mole fraction of gas A in a vapor phase, which is what we have, same nomenclature has been used as what we have done earlier. The application of Dalton's law to the vapor above the liquid we have following now. What we are doing now, basically relating P A to Y A as that what we have done earlier. For a gas A in a vapor phase, what we know is P A is equal to P total into Y A. This is what we have done. The partial pressure of gas A is related to its molar fraction in the vapor phase, and is the constant of proportionality is P total. So, P A is equal to P total into Y A. Similarly, for gas B in the vapor phase, we write P B is equal to P total into Y B. This is what we have done earlier. Gibbs-Dalton's law is basically applying the same thing, assuming that the vapor behaves as ideal gas. Extending this to the n component mixture, and for the jth component, what we know is that P j is equal to P total into Y j. This is the same thing applied for any jth component in a n component mixture. Now, if I combine Gibbs-Dalton's law and Raoult's law together to the vapor above the liquid phase, I get the following. So, if I go by Gibbs-Dalton's law, I got P A is equal to Y A into P total, all right, and the Raoult's law tell me that P A is equal to pi Y A x A. So, here I am applying the law for the vapor, here I am applying the law for the liquid component. So, you understand that ultimately I am relating the vapor component Y A to x A, which is a liquid component. This is a very important law. Therefore, I will get the vapor composition, I will get the liquid composition for gas component A. So, from here I get Y A is equal to pi A upon P total into x A, or pi A x A upon P total. Now, it is a very important thing that I am relating Y A, which is a vapor component, vapor fraction of gas A, and x A is a molar fraction in the liquid component, in the component A in a liquid form. So, basically I am relating Y A and x A, all right. Similarly, for B component, we got a PB is equal to YB into P total, and correspondingly Raoult's law gives me that PB is equal to Y pi B XB, exactly on the same line as what we did for component A. So, if I relate this thing to YB now, I will get YB is equal to pi B XB upon P total. So, basically again I am relating YB and XB in this case. So, if I just summarize whatever laws we have studied and then we can go ahead from there, the Dalton's law relates partial pressure of non-reacting ideal gases. Raoult's law relates the vapor pressure with the liquid mole fraction of a component. The Gibbs-Dalton law, application of Dalton's law to the vapor above the liquid phase, and we found that Pa is equal to P total into Ya is basically applied to the vapor now, assuming that the vapor is behaving like an ideal gas. And lastly, what we did was we combined Raoult's law and Gibbs-Dalton's law together, and it established a relationship between the vapor and the liquid fraction of a component. And this is very important law because ultimately we wanted to come to this, that Ya is getting related to Xa. Now, going ahead from here, we define much more constant now, which are very, very important from mixture perspective. As derived earlier, consider an equation with Ya and Xa for gas A, which is Ya is equal to pi A Xa upon P total. Rearranging this, what we get is Ya upon Xa is equal to pi A upon P total. Alright. What is pi A? Is the vapor pressure of component A at a given temperature T of a mixture. What is P total? Is the total pressure of the mixture. So, actually to say they are basically both constant for a given temperature and pressure of a mixture. So, if I know the temperature of a mixture, if I know the total pressure of a mixture, Ya and Xa, the ratio of Ya and Xa essentially remains a constant, alright, as long as the temperature and the pressure of the mixtures are defined. So, what we can understand from here is for a given temperature and pressure, I got Ya upon Xa coming as constant, and this is a very important finding, alright. So, the ratio of Ya to Xa is basically a constant and it is called as distribution coefficient. It distributes at a given temperature the value of A in vapor phase and the proportion or molar fraction of A in a liquid phase, and this is called as distribution coefficient and is denoted by constant as Ka. Similar value we have for Yb and Xb also, which will be denoted as Kb, but what is important to understand that Ya and Xa have a ratio which is Ya upon Xa called as distribution coefficient and given as Ka. If I want to define that thing, it is the ratio of the mole fraction of a component, let us say gas A in vapor to liquid phases in a mixture at a given temperature. So, if I know the temperature, if I know the pressure of a mixture, then Ya upon Xa at a given temperature is called as distribution coefficient and it is constant, alright. It is constant given by Ka. Similarly, I will have value of Kb. So, extending general to the jth component, I got a Ka, I got a Kb, and if I go for a Kj, for example, for a n component mixture, I will have Kj is equal to Yj upon Xj, and this will equal to pi j upon P total. So, pi j is a vapor pressure of a jth component at a temperature T, P total is a mixture pressure basically given as P total. So, again this is going to be a distribution coefficient for the jth component, which is going to be constant. So, Yj is equal to Kj Xj, which is what we know. The distribution coefficient K for an ideal or a perfect mixture is determined using the above equation. So, if I know the temperature, if I know the pressure, I can calculate the Kj value, and this is an ideal or a perfect mixture. As I say, the Raoult's law basically holds good for an ideal mixture or a perfect mixture or a perfect solution wherein there are no intermolecular forces acting, alright. But the non-ideal or real mixture, it is determined experimentally. So, there are two ways of doing that thing. One is to get experimental values, which are also distribution coefficient obtained experimentally or by empirical correlations, while one can calculate based on the ideal gas law, etc., ideal assuming that there are no intermolecular forces, and therefore, one can get the distribution coefficient theoretically also. We got one tutorial later to study if you could calculate the value of distribution coefficient theoretically and also experimentally and compare these two values, and therefore, you will be able to see what difference does it make if I calculate it theoretically and if I get the value experimentally. Alright. So, now for an ideal two phase mixture, wherein we got a gas A and gas B, the relationship between Ka and Kb also has to be made clear. Alright. So, K and Kb also get related and the liquid mole fraction Xa and Xb. So, ultimately I would like to relate in a given mixture where gas A and gas B are present, how are Ka and Kb are related to Xa and Xb. Because they are having a mixture, they will basically contribute to the calculation of value of Xa, which is a molar fraction of gas A in a liquid phase, and Xb is a liquid mole fraction of the component B. So, how do I do that? I know Ya is equal to Ka, I know Yb is equal to Kb, and I know that Ya plus Yb is equal to 1. So, if I apply the same law for vapor, we have already done that for Xa. We know Xa plus Xb is equal to 1. Similarly, we know that Ya plus Yb is equal to 1 and the Ya and Yb values are given over here. So, if I write Ka plus Kaxa, I just replace this Ya by Kaxa and Yb by Kbxb. I know Kaxa plus Kbxb is equal to 1, and this is what relates the value of Ka and Kb and Xa and Xb. So, we also know that Xa plus Xb is equal to 1, and if I therefore replace the value Xb here as 1 minus Xa, I get a Kaxa plus Kb into 1 minus Xa is equal to 1, and therefore, from here I can compute the value of Xa is equal to 1 minus Kb upon Ka minus Kb. So, if I know the distribution coefficient of gas A and gas B, that is Ka and Kb for a given temperature and pressure of a mixture, then I can compute theoretically what is the value of Xa. Similarly, I can do the same thing for Xb also. Here, if I put Xa is equal to 1 minus Xb in the above expression, I replace this value of Xa as 1 minus Xb and compute this, I will get the expression for Xp, which is Xb is equal to 1 minus Ka upon Kb minus Ka. If I know the distribution coefficient for Kb and Ka, I can compute for a given temperature or pressure what are the values of Xa and Xb respectively by this formulae. Alright. This is a very important thing. Theoretically, I will know the value of Ka and Kb. I can compute those values as I said earlier theoretically, or I can get the value of Ka and Kb which are available, the experimental data is available for a given mixture. In that case, I can theoretically compute what the value of Xa and Xb will be there for a given temperature in a mixture. So, the distribution coefficient Ka is equal to Ya upon Xa, which is equal to pi A upon P total. As mentioned earlier, K is a ratio of the mole fraction of a component in vapor and liquid phases in thermodynamic equilibrium. This is what we have defined K as. It is meaningful and defined only to two phase region. Normally, Ka is given when component gas A and gas B will be together, and then only there is basically requirement to calculate the Xa and Xp, Ya and Yb respectively for a mixture. So, normally the values are going to be defined from the mixture component gas A and gas B in a two phase region, that means from boiling point of A up to the boiling point of B, above which there is no component left as it is basically. So, we define it normally at a given pressure between the two boiling points and therefore, the two phases of the regions. For example, the mixture of nitrogen and oxygen at 1 atmosphere exists in two phases between 77 Kelvin and 90 Kelvin, the boiling point of nitrogen and the boiling point of oxygen at 1 atmosphere. Hence, normally the K is defined in this interval only. The same thing could be at 2 atmosphere or 5 atmosphere or whatever pressure which we talk about, and corresponding to those pressures we will have the boiling points of nitrogen or oxygen or component A and component B, and the K value will be defined during that temperature range. The values of K are determined experimentally at some reference pressure PO. Now, when I talk about experimental determination of these values of K, it is normally given with a reference pressure PO, which could be 1 atmosphere, 2 atmosphere or 5 atmosphere, and wherever these values are given, the value of PO will be given to you, and therefore, your actual mixture pressure could be different, which is just P or P mixture, but the values will be given for that pressure with some reference pressure which has to be taken into account to calculate the value of K. So, in the literature, the values of K are normally given in logarithmic form, and it is always given in this form log of K into P mixture upon PO, which means that if my mixture pressure is 1 atmosphere with the value 1 over here, and if I am having PO also is defined as a reference point is 1 atmosphere, then these two will get cancelled. In that case, the P mixture is going to be equal to PO, and the log K value will be given in that table in that case. So, normally it is given in the logarithmic form. from which, and once we know this logarithmic value, the value of k has to be recalculated from this expression. All right. So, this is what the experimental values will be given, and the standard tables are available, which I will show you in the next slides. The data for nitrogen, oxygen and argon are given in the next slide, and a tutorial has been solved later to understand this conceptually. So, how does this data look like? The data is given in log Kp mixture upon PO for oxygen, nitrogen as given below. So, this is what you can see. So, I got a data for nitrogen which is at 1 atmosphere, PO is 1 atmosphere, that means my reference pressure is 1 atmosphere. Similarly, I have got data for oxygen, again the reference pressure is 1 atmosphere. However, my mixture can vary from 1 atmosphere, 2 atmosphere, 5 atmosphere and whatever. I have just shown 1, 2 and 5, and corresponding to these mixtures, now I got a temperature range. As I said, the temperature range for 1 atmosphere will be from 77.4 to let us say 90, because that happens to the boiling point of nitrogen and oxygen respectively. So, the data is given as ranging from around 77 to 90, and as you can see that the high boiling component, when it goes down to low boiling component, basically this is nothing but representative value of y by x. So, as you see that as you go from high boiling component to low boiling component, the vapor component y by x go on less and less, and therefore, the value of y by x or logarithmic value goes on getting reduced, and normally what we have found is around the boiling point it comes nearly to somewhere around 1, which is what we can see later. Similarly, these values have been given for 2 atmosphere. Normally, at 2 atmosphere, the boiling point of the nitrogen will get increased, and therefore, the table has been given from 84 onwards, which may go up to 94, which may happen to the boiling point of oxygen at 2 atmosphere. The boiling point does not figure in this range for 5 atmosphere, so it comes in the next page. Similarly, for oxygen, what you can see is for 1 atmosphere, in this case, because it is below its boiling point, the logarithmic value happens to be in a negative range. That means, the values are less than 1 in this case. The values of k are normally around 1 at the boiling point, which is what we will see later. The values of k happen to be around 1. So, whenever there are negative points, they happen to be less than 1 in that case. So, at 2 atmosphere, again I got a different table, I got a 5 atmosphere, because the boiling points get raised, I got a different table. So, here you can see that the 5 atmosphere figures in a higher temperature range 94 to 108 for both oxygen and nitrogen respectively. Alright. So, this is what the values will be given as. If I just want to, again similar thing is shown for argon also, and these values have to be taken from this table 1 to 5 atmosphere, and I think this is for oxygen. So, if I want to just show it as a value of k, what you have seen in a table was logarithmic value, but if I want to show this on a graph, it is just the value of k with temperature at different pressure. So, if I say nitrogen at 1 atmosphere, you can see this is the red line, and this ranges from 90 Kelvin up to its boiling point, which is 77 Kelvin, and you can see that at 1 atmosphere at 77 Kelvin, the value of nitrogen or value of k at 77 is hitting around 1, while it has gone up to 4.2 at 90 Kelvin. Similar thing holds good for oxygen 1 atmosphere, where you can see that oxygen value at around 90 Kelvin coming closer to 1. While below 90 Kelvin, as I said earlier, it is coming less than 1, and therefore, the logarithmic value of k will be shown as negative, which is what we have seen earlier. If I go for nitrogen 2 atmosphere, because at nitrogen 2 atmosphere the boiling point will be increased, and therefore, it will possibly go from 84 Kelvin up to 96 Kelvin, and in between around this point around 90 or 84 will come the value equal to 1, which happens to the boiling point of nitrogen at 2 atmosphere. If I apply the same thing for 2 atmosphere oxygen now, it will range from 84 and go up to 96, and around this what will have is a boiling point of oxygen at 2 atmosphere, and below that the value of logarithmic value is going to be shown as negative, or the value of k is going to be less than 1. So, this is just to give a understanding of what is the comparative value of k at different temperatures and pressure. As I said, the thumb rule is if you are near the boiling point of that corresponding to that pressure of nitrogen or oxygen, it is going to be around 1. Below that is going to be less than 1, above the boiling point is going to be more than 1, and the logarithmic value of this less than 1 is going to be shown as negative in this case. So, variation is shown here for nitrogen oxygen. We found that the k decreases with the decrease in temperature for any given pressure. So, decrease the temperature, decrease the value of k. The component with lower boiling point has a higher k. So, So, this is clear that because of the boiling point being the minimum in this case, the values of nitrogen, values of K for nitrogen is going to be more as compared to other gases in this particular expression. For any component, the value of K approaches to be 1 for a given boiling point, for its boiling point. Also, the value of K is less than 1 when the temperature is below the boiling point of 1. This is what I just talked, that below 77 Kelvin, the value of K is going to be less than 1, or it is going to be logarithmic value is going to be negative in this case. So, when K is less than 1, the logarithmic value of K is negative, and that is what we saw in the table. So, with this background, whatever we have understood till now about the concept of Ya, Xa, the distribution coefficient Ka, Kb in a given mixture of gas A and gas B. In order to clear some concepts, I would like to take 2 tutorials, and once you solve this, lot of concepts will get clear. So, my tutorial 1 is, consider a mixture of nitrogen and oxygen at 5 atmosphere and the temperature is 100 Kelvin. The mixture temperature is 100 Kelvin, the mixture pressure is 5 atmosphere. What I want to calculate? Calculate the distribution coefficient of nitrogen and oxygen. Also calculate the vapor and liquid composition using the obtained K values. So, basically I want to calculate the distribution coefficient, and once you know the value of K, calculate the vapor and liquid compositions using the values of K. That is the problem. Use the data from the table given in the earlier slide. So, working pressure is 5 atmosphere, temperature is 100 Kelvin, mixture is nitrogen oxygen. This is what the problem definition, this is what the problem is given as. So, what do I want to calculate? If I want to convert that to my understanding of the nomenclature which we have been using till now is, I would like to calculate Kn2, which is a distribution coefficient of nitrogen. I would like to calculate KO2, which is a distribution coefficient for oxygen, which is what we termed as Ka and Kb earlier. I now want to give values to it. I want to give the nomenclature to it, which is Kn2 and KO2. Also, corresponding to that, I got a Xn2, XO2, which are the mole fractions of nitrogen and oxygen in liquid phases, which were earlier called as Xa and Xb. Similarly, I got Yn2 and Ya2 as the mole fractions of nitrogen and oxygen in vapor phases. Earlier they were called as Ya and Yb. So, basically I want to calculate Ka, Kb, Xa, Xb, Ya, Yb as Kn2, Ka2, Xn2, XO2 and Yn2, Ya2 in this problem, and they have to be done at 5 atmosphere working pressure and temperature at 100 Kelvin. I first want to get the value of Kn2. So, I go for the table and get the value of K at 100 Kelvin. So, if I go to the table, I get the value of 100 K value, which is given in a logarithmic form. Log of K P max P mixture upon PO for nitrogen. I go to the table, I get a temperature and for 5 atmosphere and locate the value of T is equal to 100 Kelvin, and this logarithmic value happens to be 2.004. Having done this for nitrogen, I would like to calculate what is the value of K from here. So, putting the value of K into removing the logarithmic term, what you get it PO upon P max P mixture e to the power 2.004, all right. And then what are the value of PO and P mixture? PO is 1 atmosphere, P mixture is 5 atmosphere. Put in the value of E is 1.5 e to the power 2.004, I get the value of Kn2 as 1.483. This is my distribution coefficient for nitrogen at 100 K and pressure of 5 atmosphere. Similar thing I will do for KO2 also, for the distribution coefficient for oxygen. So, for KO2, I take a table of oxygen at 5 atmosphere and I locate the 100 Kelvin in that. So, logarithmic of log of K mixture upon PO for oxygen at 100 K and 5 atmosphere is 1.042. From where I will calculate the value of KO2. KO2 is given as PO upon P mixture e to the power 1.042, and putting the value of PO and P mixture in that, again the value of KO2 is equal to 0.567. So, I got now Kn2, I got KO2. Once I know Kn2 and KO2, I will have to calculate the value of Xn2, and if I relate earlier expression, I got Xn2 is equal to 1 minus KO2 upon Kn2 minus KO2, and similarly I got a relation for XO2 also, which I will exploit in the next slide. So, once I know the two distribution coefficient for Kn2 and KO2, I can calculate Xn2. Put in the value of Kn2 and KO2 as what we have just calculated. I will get the value of xn2 is equal to 0.472. Clear? I think it's very simple and straightforward. Having done this, I can do the same thing for xO2, where I know xn2 plus xO2 is equal to 1. So, 1 minus xn2 will give a value of xO2, just put those values, and xn2 is equal to 0.472, which we have just calculated. The value of xO2 therefore is 0.528. So, I got now xn2 and xO2, and I will get value of yn2 and yo2 also. That comes automatically when I know distribution coefficient. So, yn2 is related to xn2 by yn2 upon xn2 is equal to kn2. So, if I know the value of kn2 and xn2, I can straight away calculate the value of yn2. So, just put 1.483 into 0.472 is equal to 0.66699, which is nothing but yn2, and similarly yo2 is nothing but, we can calculate in this way. Also, you can compute by yo2 is equal to ko2 into xo2, which is also known to us. Just do 1 minus yn2, I get yn2 is equal to 0.699, and therefore yo2 is equal to 0.301, and therefore I got all the values of yo2 and yn2 and xo2 and xon2, which is the vapor molar fraction in the vapor for oxygen and nitrogen, and molar fraction in the liquid, which is xn2 and xo2, which is what the tutorial asks for. Having done this, now let us go to the next tutorial, wherein we talked about a different requirement now. So, what is the next tutorial now? This is the first tutorial is just to calculation of kn2 and ko2, basically not calculation, taking the value of kn2 and ko2 from the table and relating it to yn2, yo2, xn2 and xo2. The second tutorial is now consider a two-phase mixture of nitrogen and oxygen again at a pressure of 2 atmosphere. Use the TS diagram for the vapor pressures of N2 and O2 at 86 Kelvin. So, what I want to do is get the vapor pressures of N2 and O2 at 86 Kelvin and determine the liquid and vapor composition of the mixture if the temperature of the mixture is 86 Kelvin. All right. Now, I can't use the table. This is what is basically mentioned over here, that I should use the vapor pressure of nitrogen and oxygen at 86 Kelvin, and this is basically in order to calculate the value of Kn2 and Ko2 theoretically. As you remember, in the theoretically we do not consider real gas values, operate vapor as real vapor where the no intermolecular forces are considered theoretically, and that is where this is coming from, that I would like to take a vapor pressure value of nitrogen and oxygen at 86 Kelvin. Also calculate the value of Kn2 and Ko2. That means, get the value of Kn2, Ko2 from here and compare that with the experimental data. So, the problem definition is compute Kn2, Ko2 theoretically and compare them with the experimental available value of Kn2 and Ko2. Very interesting, so that you can understand how to calculate it theoretically, which we have already seen actually in principle, how to get the Kn2 and Ko2 values and compare these values with the experimentally obtained Kn2 and Ko2, which are basically obtained from the given table earlier. So, the given is working pressure is 2 atmosphere, temperature is 86 Kelvin for a mixture of nitrogen and oxygen. And what do I want to calculate? I want to calculate Xn2, XO2, which is the mole fraction of nitrogen and oxygen in a liquid phase, Yn2 and Yn2, which is the mole fraction of nitrogen and oxygen in vapor phase, and Kn2 and Ko2, which are the distribution coefficient of nitrogen and oxygen respectively for given temperature 86 and pressure 2 atmosphere. So, how do I go? How do I start? As I said, I am told in the problem or the tutorial that I have to take a vapor pressure of nitrogen, let us say at 86 Kelvin. So, corresponding to that, I will get these values from the TS diagram, and if I locate the temperature of 86 Kelvin in these, corresponding to this value, I can read the pressure. So, this is basically saturated vapor curve. So, this is a basically two phase equilibrium with the gas and the two phase, the coming vapor and the liquid are coexistent, they are in thermal equilibrium on this saturated vapor curve, and therefore, wherever this horizontal line hits or intersect this saturated vapor curve, corresponding to that, whatever is the vapor pressure at 86 Kelvin, and therefore, this happens to be at 2.517 atmosphere, and this is the vapor pressure of nitrogen at 86 Kelvin, and this is what I require, which is my value of pi n2. This is a function of only temperature, and the vapor will exist only up to the critical temperature of the nitrogen. All right. So, therefore, vapor pressure is given normally below the critical temperature of a given component or gas. Following the similar procedure for oxygen, we have the vapor pressure for oxygen also, which happens to be 0.64 atmosphere. Alright. So, pi N2 is 2.517 atmosphere, and same thing is repeated for oxygen, pi O2 is 0.640 atmosphere. So, having done this, I can now calculate the value of K N2 as P total pi N2 x N2 pi O2 into 1 minus x N2. These are the values which have to be theoretically applied. X N2 therefore is equal to, algebraically I will get these values. Putting these values, I will get x N2 as 0.724. Alright. So, what I know is vapor pressure of nitrogen, vapor pressure of oxygen at 86 Kelvin. I know the value of x N2, and I can compute therefore the value of x N2 depending on P total and the value of vapor pressures over here. So, I get x N2 is equal to 0.724. Similarly, XO2 is 1 minus x N2, I get x N2 as 0.724 and XO2 as 0.276. I will get the value of pi N2 in the same way, where I know the total pressure, I know the pi N2, I know the x N2. Having done this, I will just put those values over here, and y N2 is calculated as 0.911. So, once I know the pi N2 upon P total, which is what we have calculated, I can relate that y N2 with x N2. Similarly, I can get YO2 as YN2 plus YO2 is equal to 1, and 1 minus YN2 will get YO2, and therefore, YO2 is 0.089. I can get the value of KN2 by just finding out the ratio of YN2 upon XN2, because the definition gives KN2. Putting those values here, I will get the value of KN2 to be equal to 1.2583. Understand that the value of Kn2 has been computed at 86 Kelvin, which is above its boiling point, and therefore, value of K is more than 1.25 here. And similarly, the value of KO2 is going to be 0.089 upon 0.276, which is 0.3224. Again, understand that the value of KO2 is computed at 86 Kelvin, which is less than its boiling point, and therefore, it happens to be less than 1, which is 0.3224. All right. So, calculated, if I want to see the value of K calculated, which is y upon x, and I get calculated value of Kn2 as 1.25 and KO2 as 0.3224. And if I take the similar values from experimental now, I can see the experimental values of Kn2 are 1.2335 and KO2 is 0.36. So, you can see that the difference between the two values, theoretically calculated, experimentally calculated, difference is not too much, but there is a difference, and therefore, sometimes this experimental data can be taken, sometimes this calculated data can be taken, but it is not possible to every time calculate the values, because some values may not be available, or it is not possible sometimes to have all the experimental data available in your table, and therefore, the compromise may have to be done for a given range of temperature. So, if I compare these two, the difference is basically owing to the ideal values differed from the experimental value by a small amount, and this is because the effect of intermolecular forces is neglected in the ideal mixtures, and this is what I have been talking about earlier. So summarizing my lecture today, what we understand is Dalton's law relates partial pressure of non-reacting ideal gases. Raoult's law relates the vapor pressure with the liquid mole fraction of a component in a mixture. So, Ya is getting related to Xa. Gibbs Dalton's law is an application of Dalton's law to the vapor above the liquid phase, which is what we understood, and we found that distribution coefficient K is the ratio of mole fraction of component in vapor to liquid phases. So, K is equal to Y by X. It is meaningful and defined only in a two-phase region of a mixture. All right. This is what we did. I got a small assignment for you, which is for a nitrogen oxygen mixture at 1 atmosphere and at 80 Kelvin. Please find out the vapor pressure and compare the data with experimental value, and these are the answer for that. The problem is given to you, these are the answer. Please solve the problem for yourself. Thank you very much.